Okay, so your assignment number 1 was due yesterday, and I'm going to give you the solution very soon, either later today or maybe tomorrow. So you can definitely take a look at the solution and compare with yours. If you got any concern, let me know. Okay, we can talk about it. And the exercise that we did from last time, which is about a hybrid sorting algorithm based on doing insertion first, followed by selections. So that one is quite an interesting one because it's really based on your understanding about doing insertion sort versus selection sort. So I posted like a very detailed walkthrough about how this exercise can be thought about and solved. You can think about that's more like a very like a one example kind of question that would require some deeper thinking. So this is where you can find it. So you can just go under exercises over here, and then you see analyzing hybrid sorting algorithm. So I encourage you to take a look. Right? So this exercise is definitely covered in the lecture material. Right? I just want to dive directly into linked list today, so we don't have to work on that today. All right? So make sure you study that for your later test and also for the exam. All right? For that one there. Okay. And then for your assignment number 2, according to the calendar, let's take a look, to see where we are. Okay. So if you go to the lecture site, let's look at the calendar, right? We're still following strictly the schedule, right? Let's take a look. So we're now in lecture number 9, February 3rd, and your assignment number 2, based on linked list, will be released next Monday. If I can release a little bit early on Sunday, I can definitely do that. You can just take a look at the starter code, want to get a little bit, I guess, get started earlier. It's up to you, but I'll try to see if I can release a little bit earlier. But assignment number 2 is definitely going to be about linked list. Not too much recursion. That's what you did for assignment number 1. And you really want to watch out the timeline here. So I would suggest once you get the assignment next Monday, you really want to move forward with the progress as much as you can. If you can finish that even before the reading week, that'll be awesome. And I'll give you guys also a guide and also some practice questions for your upcoming programming test, which will happen, you can see, on the 26th. It's actually the Thursday. Oh, yeah, it's the Thursday after the reading week, right? I think we can maybe try to schedule maybe some kind of like a review session, extended office hour, to see whichever that might work for you. I'll announce that. Either way, you can definitely get a chance to talk to me if you got any question about from studying for the test. But just notice that programming test will be on the 26th during the lecture time. But we are not meeting here. We will be meeting in Williams Small Center. I'll send you the exact details closer to the time. Okay. So everything will be clear to you next week about what's going to happen. So today we're going to start covering lecture number 9. We'll start covering linked list. So there will be 2 kinds of linked lists. One will be singly linked, which we'll start today, and also doubly linked list. And ideally, I'm hoping to finish covering singly linked lists in lecture 9, 10, and 11, possibly about more than halfway through. And then doubly linked list just has some small extension to singly linked list. One lecture should be enough. So we are hoping to finish everything about array linked list has entirely upper bound before the reading week. After the reading week, there's only one focus about lecture material, trees. So we're going to cover lots about trees. It's definitely something might be most likely new to all of you, most of you. So we definitely have to spend time going through not just about the theoretical stuff, but also see how we can implement stuff in Java as well. Right? So that's something we can look forward to. Trees are a very fun idea that also can lay a very good foundation for 3101 as well. All right. All right. Any questions? Any concern? Any questions? All good? Okay. Let's now start talking about linked lists today. Okay. So we'll start from slide number 10 for the lecture. All right, so this is something you want to keep in mind. So you can think about whenever you talk about fundamental building block for data structure or for algorithm, array is definitely one of them, and array is something we have learned so far. So they are very good in performing for indexing. You just want to go to a particular position in the array, but they are very bad if you somehow want to involve any shifting operation for inserting or deleting, right? You want to create an empty slot in the middle and shift everything to the right by one position. That's really the bottleneck for insertion sort, right? That's something we spoke about last Thursday. Just keep that in mind. And what we want to do is we want to talk about some alternative data structure. However, keep this in mind. There's no silver bullet. I'm not saying linked list should be the way to go, and you can forget about the array. Not really. you have to somehow decide when to use array and also when to use linked list. I'll talk about that kind of comparison at the end of the linked list lecture. For now, you can just just focus on learning about linked lists, and then we'll see how things will go. Okay. Today, I just want to give you some intuition, very important, about some visual clarification about what a linked list is. And of course, we're going to rely on your knowledge from 2030 about reference aliasing, right? That's something we need to do. And then I definitely want to get to some Java code as well. I will trace the code together with you, see how things will go. It will definitely help on the assignment number 2. Okay? But of course, stop me anytime. Okay? A linked list, by definition, is simply a series of connected nodes. So what really connected here really means, right? That's something we'll see. And then it's a linear sequence. I'll also explain what linear versus nonlinear. That's something I want to just give you a very quick note about what linear really means. But we're going to compare that when we get to the tree after the reading week, right? You will get 2 chances to learn about it. So at the runtime, connections are through reference aliasing, right? Reference aliasing, very important. Let's now talk about some intuition about linked list. Definition, a linked list specifically will study about singly linked list, which means the way they link is following one direction only. You can think about always to the right, to the right, to the right. Okay, so let's highlight this part here, and then we'll talk about it. A chain of connected nodes, and then we got to rely on aliasing. Okay, guys, quick question. Looks like a review question from 2030. What exactly is aliasing? Can you just intuitively describe it? What's aliasing? Give it a try.
When 2 objects are pointing to the same variable?
It's pretty good. Or to be more precise, you're saying maybe more than one variable storing the same address of some objects, right? That's very good. Okay, on the right direction. This will be a very important concept for linked list. In some way, people think about linked list is actually more tricky, trickier to get right than array. But you do have some advantage as well. That's something we'll see along the way. So aliasing over here is really about, let's write down this intuitive definition. When you get multiple variables storing the address of the same objects. Okay, something we'll see visually very often. So I'm not visualizing it just yet. We'll see that. All right, a chain of connected nodes. But let's now just build a chain very quickly, a sequence basically. So what we have is something like this. Each node looks like this. Think about this more like objects, and it's going to be of type node. And we'll talk about this node class a little bit later today. But for now, I want to give you visual, like an intuition. Each node can be thought of as divided into 2 parts for the information. One part is for the data. Another part is where we're going to make the connection work. So there will be 2 attributes you can think about. One part here is called data. And another part there is called the next reference, but it's for data. Let's say we got a chain of nodes, and each node stores some string value. Let's say the first node stores Alan, just a name. And this node here may have some reference to it. For example, it could be the node here, simply the address is stored in variable n. Right? You can think about n data would be just Alan. Okay. You can think about n data, and then it would just be as Alan. Of course, if you call the equals method on the string, you can say n.data equals Alan, it will also be true, right? So that's so far so good. Well, it would be very boring if there's only a single node in isolation. The way it works is you can build as many as you like in the chain, okay? So the way to do it is there is another attribute there called next. That one there is just going to point to another node. So this is where the tricky thing can be, the tricky part about linked list. But let's just build it here. And this next node over here has just the same structure as the previous node. They are instantiated from the same node class. So this one here, also we got data, let's say followed by Alan, we got Mark, right? And possibly we got another one over here, also next. And then this will be just another node. I think I'll just get a chain of 3 nodes. And then we got data here for the third node. Let's use Tom. Question for you. Let's say that'll be the end, the third node. What should be the value for the next? If I say I don't want to connect anything further.
No.
No, exactly. The default value for reference type, right? Also keep that in mind. It's very important to always remember, especially for syncly linked list, what the next node, what the last node is like. All right, right here, this part over here is going to be null. Okay. So think about this one here is the current last node in the chain. Last node in the current chain. All right. So far, so good. And then let's now do a little bit of manipulation here. Okay. So we already talked about n here. N is the first node. And typically, we may actually want to call the first node with some special name. Right? So the name we're going to call that is called head. It's called the head of the list. Of course, if you decided to insert something in the beginning of the chain, the head is going to change. That's something we'll see. All right. So let's now, given this, let's do a little bit of manipulation. So let's say here, let's now manipulate the second node. Maybe the first node first. Okay. I'm just going to write down some Boolean condition, and you can just tell me whether it's true or false. All right. If I say n dot next not equal to null, is it true or false? True, right? Because you can see that n dot next is referring to this particular object. It exists, so it's not equal to null. Of course, it's true. All right. And then, of course, you can also say n dot next dot data. What should that be over here, according to the list? And next, the data, that should be mark. All right. Okay, let's just do one more. Okay. Let's talk about this one here. Let's refer to it. How do I refer to the last node? Starting from, because the only reference we have is really from here. Right? So if we say n the next, and the next, that one there is going to give us this particular node. Okay. And sometimes we also call it tail. You can think about, right? We also say that's the tail. We're keeping these two references usually at some class level, but we'll see in the implementation. You can think about this one here is simply equals tail. They refer to the same object. That's really reference aliasing. So either you can go from and the next, or you can simply go from the tail. They really refer to the same objects. That's reference aliasing. Okay, one more. What if I say the following? And the next, dot data. What happened if I try to evaluate it? Anybody? Yeah, go ahead. You'll get an error. I agree. What kind of error? I agree, something to do with null, right? Because, yeah, Daniel? Yeah, you get a null pointer exception, right? That's the number one common mistake you will run into, I'm pretty sure. Okay, but hopefully you can get away from that more before you complete this course. So the way to think about this is you can think about this part here and next. So and next is going to give you null. And then you kind of call data on the null pointer exception. Okay, okay. Hopefully you're following. So this one here is going to give you null pointer exception. Typically, you will see that in the assignments. The way null pointer exception is going to come out is not really in this kind of very explicit context where you got a very obvious list. You simply say something dot next, dot next, dot next, and count how many times you have. Not really. Usually, it will be in the context of a loop, which we'll see later. So you got to be very careful when you actually program the loop, when you are trying to manipulate linked lists. You got to watch out very carefully about the update condition, Boolean condition, etc. That's something we'll see once we get to the code, hopefully Thursday. We got head and tail, right? Head and tail, first and last node. And there's something called linear collection. I wouldn't spend too much time on that. I think it would be more appropriate when we actually talk about linear versus nonlinear when we get to the tree lecture after the reading week. But for now, whenever we talk about linear collection, okay, what does that really mean? So linear, in this case, simply means we got unique successor. Okay, I'll write it down and I'll explain what that really means. Each node in the chain has a unique successor. Successor means what follows that. So for example, if you look at this node over here, the only way to go to the next node is by following the next reference, and you can only get to here. That's the only one. You don't have more than one node you can get to by using the next reference. And again, from this node here, the only way you can get to the successor, what follows that would be following the next reference, and there's only a unique successor, and etc. Right? Successor. Right? Once we get to the doubly linked list, we also got something called predecessor, but it's not for singly linked list, so you don't need to worry for now. Okay? That's what linear really means. But once we get to the tree after the reading week, we'll see more clearly about linear versus nonlinear later. And let me also talk about this very fundamental difference between the array and also singly linked list. It's really about absolute indexing versus relative positioning, right? Let me highlight them, and then I'm going to visualize it. It's also very important to clarify that. So we basically got, one is called absolute indexing versus relative positioning. So what you really want to pay attention to as a keyword is the absolute versus relative. Okay, we'll see exactly. Okay, let's now take a look what that really means. Oh, sorry. And this kind of like absolute versus relative indexing really kind of explain many of the scenario where we can see the bottleneck for either of the data structure. Okay, so let's start with array, which is something we know pretty well. So we start with absolute indexing of arrays. And I'm pretty sure all of you have taken maybe the C course 2031 or 2032, right? So let's now review. Well, not really review, just remind ourselves. When I say array A at index I, this one, first of all, I can go to a particular position in the array directly. That one there is a constant time operation, big O of 1. Simply because if you look at just the A here is the starting address of the array, right? Just go a little bit more visual, right? Let's say this is my array A. And I may have different indices, let's say 0 here and 1 here. So if I look at A here alone, it's about starting point of the memory block for the array. And the I here can be 0, can be 1, can be 2, etc. That really means about how many units of offset you want to go beyond that starting address. Let me write it down and I'll show you why. Okay. So here will be the number of units for calculating address offset. You know, for example, let's say this array here is storing integers. So we got 23, 46, etc. Now, if for the index 0, that simply means we don't have any offset. You can directly go to where A is starting from. Just go there, and you can get 23. How can I get to 46? In that way, you want to know how long this particular element is. It depends on the type of the element you're storing in the array. For example, it will be 4 bytes for integer. In that way, we're saying that starting from here and go for 4 bytes, and then you get to here. It's about calculating how long you want to go in the memory block. But this calculation here is constant time. It's not costly at all. Okay? So just a little bit intuition about why array indexing is actually a constant time, big O of 1. Okay? All right, so what about linked list? That's something we want to get to. It's called relative positioning. Let's get to that part. Relative positioning of, let's say, singly linked list, but it also applies to doubly linked list as well. But let me just say singly linked list, since that's what we're talking about. It's relative positioning. And before we draw the conclusion on the running time, let's visualize what's happening. And then you will be able to answer this by yourself without me telling you. Okay? So let's now just rebuild the nodes like how we did earlier. Let's say we have a chain of 3 nodes, like 4 nodes. So I start with the head, and then I got some node over here, right? And let's ignore the data part. It's not important. For me to get to the second node, I need to go to the next. That one there is going to lead me to second node. And if I go for another next, that's going to lead me to just one more node right here. And if I go for just one more, it's going to be like that. And that will just go to null. Let me just draw just this one here a little bit better. Right, next. And if you think about the positioning here, let's say we also start a position for linked node with 0. Conceptually, this will be index 0, index 1, index 2, and index 3. Makes sense. Let's say we want to define a method in Java. And the way we use the method goes like this. I have some, let's say I have a list, like a linked list. And I say I want to get the node at certain position I. And you can think about the I over here will be somehow larger than or equal to 0, and also should be strictly less than the number of nodes that's in the list, right? Just how we figure out the length minus 1 for the array indices, right? Similar. So what will be the worst case in this method here? Or it's really the same. There's no worst case. Daniel, go ahead.
There's a worst case if the node is at the end.
Well, very close to the end. For example, let's say I here is simply around the length of the chain. In that way, how can you get there? You have to go follow one next reference, another one, and also another one, all the way to here. You might be arguing, yes, we may have tail right here, no problem. But if you want to go to the second last node, you have no shortcut. You still got to go there. So the number of next references you have to inquire may just be linear. In that case, you don't have a cheap method to achieve this. Okay, I'll write it down. So what we want to see from here is for the I, okay, right here. The worst case, when I is very close to n. And the n here is the number of nodes in the chain. And this n here will just boil down into the number of next reference lookup. Okay, so I may have to go for 1 here, 2 here, and also 3 here to get all the way to the end. Right? So that's the bottleneck for the singly linked list. And we say that this is a relative positioning because we just cannot go directly to some reference here, but we cannot. We have to say starting from the beginning and then just go for as many references as you like to get to that particular position. It's relative to the beginning. So as we can see from here, relative positioning is going to be a linear operation. Okay, so now we have a very clear contrast over here. When you talk about going to a particular position in the linear collection, either in the array or the simply linked list, in the case of array, constant, calculating address only. But if you talk about linked list, not really. You have to start from the beginning, go all the way to where you want to be. But if where what you want to be is very far from the beginning, in that way it will be expensive, up to linear. Okay. Question so far? Today we wouldn't go over that many methods about manipulating the linked list, but I think this kind of visual really give you a very important idea about how things will work. Okay, so after this, before we do something about the various operations visually, let's now see the slides if I miss anything. Okay, we got two references to the data and to the next node, a relative versus absolute. All right, so what I want to do now is this. So this one is also a very important point. Whenever we want to create an array, we have to give the exact length of the array, right? So you're going to say something like, if I try to create an array in Java, I got to say integer array A will be new. Integer array, and I have to pass some value over here. You got to determine what the size is. However, in the case of a linked list, you don't have to. You can even start with no node in the chain and gradually add it as you go. So the number of nodes you can add to the chain is unbounded. You're only bounded by the computer memory, basically. Okay. It's also a very important point for you to remember. So what I want to do now is to see how we can perform the various operations about insertion and deletion and get an idea to see why inserting and deleting from linked list, some of them are simply just way more efficient than doing that in the array. We already know if you want to do insertion, deletion into the array, it's linear always because you got to involve the shift operation. But for the linked list, not necessarily. So what we want to do is let's start with something visual. Of course, all these operations will be turned into Java implementation. So that will be something we can go over a little bit, some of them in the lecture, but it's mainly something you have to do in the assignments and also something you have to be able to do in the programming test. Okay. Let's start with insertion. Let's say we got a chain of nodes. Let's say we got a head and also we got tail. First node, second node, third node, and fourth node. And the fourth node, the next will just be null, right? Exactly the setup that we spoke about. Let's say we talk about insertion. And we'll talk about three different scenarios. We'll talk about how you can insert this particular node, let's say Toronto, into the beginning. And then let's just start with this, and then we'll see how that will work. At the moment, you can see we got this is the beginning. But we don't want it to be the beginning anymore. What we want to do is somehow we want to have another node here. That one there will store Toronto. And then we want this node to become the first node in the list. At the same time, the head should also be pointing to this node instead. Apparently, we also want to make sure the connection from here is pointing to the old head. So these are the steps that will be involved. Visually, it's very easy to see and draw. But the problem is, how can we turn that into Java code? Let's try to write some steps. I think that can help, right? This one here, let's do, I'll just give you some guidance, okay? Step number one, apparently we got to create a node first, right? The new node. Let's say label, okay? So step number one, we're going to create that new node. The data part is going to be Toronto. And in the beginning, let's say no connection whatsoever just yet. So the next reference will just be null. And let's call this node here with the name T. Of course, the corresponding Java code you have to write is using a new keyword to create, right? That's something we'll see a little bit later today. Step number 1, create a node. And step number 2, let's try to make sure the next of t is no longer null. We want to let it point to the old head. Let's do that, second step. So second step is going to be t dot next equals head. That's pretty much Java code already. So what that will do is, rather than pointing to null, it's now going to point to wherever the head is pointing to. That's what this assignment is doing. That's something I assume you guys know about from 2030. Right? If you really got trouble understanding why this way we can create aliasing, you should really reach out to me as soon as you can. Right? That's so important. What's left to complete the steps for insertion? Sorry? The new head? Yeah, I agree. Would you like to suggest some code to write? It's simpler than you think. I agree we should set a new head to be t. Yeah, exactly, right? It's nothing complicated. Oh, another tip I want to give you guys right away. So recursion, when you want to design a recursive method, you can draw some recursion tree to start with. That's what I said earlier. Fine. But for linked list, I would say it's even more the case. Whenever you want to design some algorithm or methods, draw is really the best way. Okay. All right, so number 3, as your fellow student correctly said, is going to be head equals t. All right. So head, rather than pointing to the old head here, is now going to point to t. After all these 3 steps, what we have is the head is now pointing to Toronto, and Toronto is now pointing to the second node, which used to be the first node. That's inserting to the beginning. That's it. Now, without seeing the actual Java code, just by this visual, what's the running time for this? In the case of array, we know that it's going to be linear because we're going to shift everything to the right by 1 position. But how about this one? Because of 1? We don't even see a loop, right, over here. It's all about 1, 2, and 3. They are just about some primitive operation. So just a big of 1. Okay? So this is why, in some cases, inserting to the beginning, sometimes inserting to the end, is usually just a big of 1. There's an important question for you guys to think about. Whenever you want to write code, sequence matters. For all the operations I'm going to say about beginning, middle, and also end, step number 2 and step number 3, you want to think about an important question. Can we swap them? I'll write it down first. You want to think about. Okay. Swap 2 and 3. What I'm saying is, can I do the following? After creating this new node, I'll try to set a new head. And then I'll try to set the next for the t. Can I do that? The answer should be quite obvious. Would you say yes or no? Would you like to briefly describe so we can also let your fellow student know?
Because you will lose the start of the linked list.
Exactly.
Mm-hmm.
Right? Yeah, for this one, let me hand wave a little bit. Right? If you do this one first, that means the head is already pointing to t. And when you execute this, it's a 3rd step. So now t dot next should be set to the head, which will be itself. It's not really properly setting to this LAX node. So can we swap 2 and 3? No. All right. So of course, you got to organize your thought a little bit better, to maybe write it down on a piece of paper or on your notes to make sure you can explain that properly. All right, that's about inserting to the beginning. Let's say we want to insert to the end. Let's make some assumption. Let's say insert after. Let's say we have, so what we want to do is we want to insert to the middle, let's say Vancouver, okay, to the middle of the list. And let's say we want to insert after, just to make it a little bit easier. And we make the following assumption. Let's say we are given this reference here, which is called n. So assume to be given. We assume. You think about it, it's like a parameter or argument for the method, for insert to the middle. What we want to do is, we somehow want to insert a new node containing, storing Vancouver, maybe somewhere here, containing Vancouver, after this node. So visually, what should be the connection? This one here should be pointing to here. The next reference should be pointing to this node. This connection is no longer applicable. That's what we're doing. Can we see that visually? But now how do we write some steps down? Let's now do that again. Step number 1, create a node first. That'll be the easiest one, just do something. So what we do is, number 1, I'm going to create a new node, storing Vancouver. So that will be Vancouver. And then the next will just be null. And eventually, we actually want to build the connection like this. So this one should point to the new node, and the new node next should point to here. Now the question is the order. All right? Okay? So step number 2 should be like this. Since you guys are just starting to see it, so I'm just leading a little bit fast, but you definitely should really slow down when you actually study for this and make sure you're really convinced about every step. Step number 2 should be right here. We say, let's call this node here that we have created called V. You want to say v.next will be assigned to what? Say it again, please. Yeah, or n.next. Because NSP is actually what? Conceptually, I know what you're saying, but NSP is more like a data, right? You really meant to say n.next. Okay, very good. N.next. So what that would do is, rather than pointing to here, it's going to point to wherever n.next is pointing to, right here. I think this one I can draw a little bit better. Right? You can think about n.next and v.next. They are now aliased to the same object. But don't worry, we're going to fix the link very soon. That'll be step number 2. Step number 3. We want to make sure this guy here is gone. Gone to where? It should point to V, right? Number 3, n.next will be assigned to V. So these are the 3 steps. And that's going to, rather than pointing to here, is going to point to wherever V is pointing to. So what we have is, we still have the head right here, go to next, go to next, go to the next, go to the next, and so on. So it's really an expanded chain. And similar question, can we swap 2 and 3? The answer is you cannot, for similar reason, right? So that one I'll leave as exercise to you. Similar reason, you just cannot. The order really matters. So don't be too surprised. For example, in the test word exam, I might just give you some suggested sequence of Java instructions, and I kind of ask you whether that will work or not. You want to be able to judge and also explain. Let's do one more, and then we'll take a short break. And after the break, we can do deletion. Let's say we want to insert to the end of the list. Let's say Montreal, and then to the end. This one will be kind of similar, right? We got to create a node, and then we got to make sure this one here will point to the new node, and the tail should point to over here. Similar to insert first, very similar. Okay, let's do that. First of all, we create a new node. Let's say the new node is called M. And that one there will be Montreal pointing to null by default. That'll be step number 1. So step number 2, you have to make sure this is now pointing to this node over here. What used to be the last node should become the second last node after the insertion. So step number 2, tell the next equals M. The final step, we want to make sure tail is now correctly set to this new node. So number 3, the tail is assigned to M. Again, 2 and 3, you cannot swap them for also, again, similar reason. We'll actually review many of them in the actual Java code, where there might be a very important critical step of certain algorithm for linked list. But it's so important for you to get the visual intuition first. So later on, it's a matter of translating them into Java code, which is not difficult. You just want to get used to this workflow. Why don't we take a very short break, and then we'll continue with it. Okay. All right, let's do just 2 more operations for the deletion, and then we can talk about some Java code and do some tracing. Okay. This one here about removing from the end, I'll leave as exercise. It's very similar to what we're going to talk about for the previous 2. But let's talk about the previous 2. Let's say we want to remove certain nodes. To start with, let's say we want to remove the very first node. The very first node is LAX. That's in the beginning. Conceptually, removal may be even easier to draw. You don't even have a new node to be created. In this case, you want to make sure this is removed. At the same time, the head should be pointing to what used to be the second node. That's removal. But how do we do it? That's the tricky part. Visually, trivial to draw. But in Java, in any programming language, you got to be precise about a step. The way to do it, this one here, let's do it together. I will need some temporary variable, at least for my implementation. Let's say we got some temp, which is alias to the current head. What that will do is, I will simply say the temp variable storing the same address as the head. So they point to the same objects. Step number 1. So I can use it. So now, after I've done this, I don't mind losing the reference for head because I still got temp. Step number 2. I can say the head right now should be, rather than this first node, because that should be removed, it should be pointing to the current second node, which will be head.next. Of course, you might be thinking, can I actually replace the head over here by temp? Yes, you can. Because at this point, they point to the same object. It's fine. So what that will do is, it's going to say head, rather than pointing to here, it's going to point to the next node right here. Technically speaking, up to this point, things might just work because the head over here is already pointing to the second node. However, for conceptual cleanness, you can see that now we actually got 2 nodes pointing to the same node. It's not a good practice. You might run into some maintenance issue for your linked list in the long run. So it's really good to clear that. So the third step, we want to make sure this node here is not really connected to this node anymore. That one's supposed to be deleted. So once you actually set this reference to be null, the garbage collector that's going to be automatically done by Java will come in place pretty soon. So number 3, the temp dot next should be set to null. So that means this one here is gone. So this node here basically will be in isolation. It will be garbage collected pretty soon. Of course, if you try to program this kind of deletion in let's say a language like a C, you will have to make sure you free the memory explicitly yourself. But for Java, we don't have to. That's the advantage. All right, so that's about removal from the beginning. Now, most important operation, right? Oh, by the way, for this one here, you can see it's still like a constant time operation, no loop. But now let's see the next one. Let's say we want to remove something in the middle, Atlanta, ATL. So for that one there, let's say I want to remove, there's one here. That'll be somewhere in the middle. Not exactly the end, but just somewhere in the middle. Conceptually, visually, I want to remove this node, which means this node here should point to its next. Other than that, no head or tail should be reset because I'm in the middle. But this operation here is not as trivial as you might think. In order for us to do that, since we only got a next reference, let's see this. To start with, let's say the input to the method we are trying to implement. This is n, which will be the node to remove. Let's say you're only given this reference here for n, pointing to Atlanta. Is it enough for us to somehow do the removal? Let me make it more explicit. It's like hints. If I know that this is the node I want to remove, what will be the next reference to set? For example, here, because I got to make sure this next is no longer there. It should be set to n.next. Now the problem is, where is this node? If you are not given this node, what would you do? Remember relative positioning, you're exactly right. So guys, here's a constant, very important line, right? Here, whenever you want to remove from the middle, from the linked list, if you're only given the node to remove, in singly linked list, in order for you to set the previous node's next reference to next, either you're given this previous node directly, which is not very common. You wouldn't be given that node. In your algorithm, what you have to do is you somehow want to calculate what is the previous node for the node you want to delete. In that way, as you said, you have to start from the beginning and go all the way to somewhere here. We'll see exactly what the conditions you set. But let's say for you to find this node, what will be the running time? N. Relative positioning, because this previous node might be very close to the end of the list. So it might be still linear. That's something we'll repeat again, but I want to give you some sort of line to you right away. Okay? Let's now assume. Let's say this previous node is also given. However, you want to keep a note to say this is really the bottleneck for performance. Exactly how, we'll see once we get to Java code, either Thursday or maybe next week, Tuesday, either way. Let's say we're given this previous. So once this is given, so now we can do the thing. Step number one. So step number one, we're going to say the previous the next will be n.next. So what does it do exactly? Previous the next should be set to n.next, which is here. So that should be set to here. All right. So previous the next, not here anymore, is going to be set to n.next, which will be right here. That'll be step number one. And then step number two, we're basically done. We got to make sure this node here is also not really pointing to here anymore. It should be garbage collected. We want to make sure, delete this reference as well. So that'll be step number two. And next should be also set to no. So these are the two steps. But here we're just being a little bit generous because the previous was simply given, but there should be some loop to actually calculate the relative positioning for the previous. That's something we'll get to a little bit later. Exercise for you. How can I remove the tail, the Boston? Think about the step, right? Exercise. Shouldn't be difficult. This one here, which is Boston. Exercise. Any questions so far? All right, hopefully that can give you enough intuition about how we are supposed to manipulate the linked list. But before we get to some concrete, like a method, algorithm to discuss, let's see how we can create a list. Let's do a little bit Java code. Not on Eclipse, but on the paper. I'll make the code also available to you, so you can also play with it before we release assignment number 2 next week. So let's take a look at the slides. Oh, here, right? So slide number 12 will be the node. So this node here will be very close to what you will receive as a starter code in your programming test. Not exactly the same, but very close, except that this node here is not generic. You store string values always, but I'll talk about generics a little bit later. Okay? So there are two classes you have to pay attention to. One is called the individual node class, and also we got the overall singly linked list class, in which we got the head right here. Of course, for your own implementation, you can also add a tail as well. It's kind of up to the implementation. So these are the two classes we're going to go over first, and we'll see how we can build the chain of nodes from scratch. Okay, let's take a look. Let's now just dive a little bit into these two classes quickly. The top level is singly linked list. And I'll visualize it in just one moment. And then you can see that for now, we only got one attribute called head. And notice that the head has the type node. This node here is referring to the second class right here. Okay, so they are somehow related. Let me start with, what if I want to create a new singly linked list? So what I do is, of course, I use a constructor, but visually, some list L stores the address of some objects of type singly linked list right here. So singly linked list. And there's only one attribute called head. So what I will do is, I will put a head attribute here. In the beginning, it might just be pointing to just null. So this is the visualization of an empty list. Meaning that the head is not pointing to anything at the moment. So the chain is simply empty. No nodes in the chain, just null. Okay, let's take a little bit, take a quick look on the node itself. So we get to the different methods like a get size, get tail, add first, get node, etc. That's something we'll talk about from Thursday. How about the node class? Let's assume we actually store data as the next. Oh, sorry, data as the value. So what I will do is, let me show to you right here. So this will be element, just string, make it simple. And also we got our next reference. You can see that the node here is simply corresponding to the class name itself, which is totally possible. For example, in 2030, you may have maybe seen some example, let's say the marriage example. Let's say in the person class, you have an attribute maybe called spouse. What's the type of spouse? Also person, right? Similar. Okay. Whenever you see that an attribute simply has the same type as its enclosing class, we say that recursive type. Just for your information. So a type simply refers to the class itself. It's called recursive type. And the constructor here will simply take the data and also the next reference. So you can think about the n here is going to be set for the next. Right? Everything else will be quite straightforward, standard. Get element, get next, and set next. Okay? And let's just visualize one. So whenever you want to create a new node, what you would do is, let's say n here, and then of type node, where we got elements and also next. And the element might point to some string objects over here, and the next will just point to the next node. The reference of some node. Of course, if that will be the end of the chain, you simply put null. It depends. And how do we connect the singly linked list and also the node here? Let's say, if this is the beginning of the chain, what we'll do is we're going to call this method here. You're going to set the head. So I can say something like L dot set head. And what should I pass? N. Once I've done that, I'm going to, so n here will just be the n here, right? Aliasing. Rather than pointing to null, it's now going to point to this node here. After this, we have some aliasing. Either you say l.head, or you can say n. So these two references simply have the same value. Right? You can easily check it on the debugger, right, to compare the addresses. Question so far? Just remember we got two levels for the syncly linked node. We got a node level and also list level. So list level, to really get connection, just set what the head should be. And sometimes you may have to set a tail as well. We'll see that later. All right, so having the fundamental cover, let's now try to see how we can build a chain of nodes. We got two different approaches. I want to show you both. You can definitely choose which one you would like to do in your assignment or in your own practices. Let's say this is the list we want to build. So we got Alan, followed by Mark, followed by Tom. So Alan should be the first node, followed by Mark, followed by Tom. And this is the node class that we had earlier. Should put that as a reference here. Let's not involve the syncly linked list just yet, just the node. And these three lines will do. We try to create Tom, Mark, and Alan. Somehow this is necessary. Tom here, and then we create Mark here, and then Alan and here in the reverse order. We'll discuss a little bit later whether or not you can do it not in the reverse order. We'll talk about it. Okay? Let's now go line by line. Line number 1, right here. Okay? So what we're doing is we are creating a new node of the name Tom. So that means Tom is now going to point to this node objects right here. And we know that for every node objects, we got elements and we got next. Elements and we got next. Let me just copy this because we need another 2 nodes to be created. Copy. Okay, good. And in this case, you can think about we're calling the node constructor right here. And then we simply replace E here by Tom, and also N here just by null. And that one is going to set the element and next accordingly. Right? You know that kind of tracing from 2030, right? So you can see my point. So element here should be set to Tom. And the next should be null. So that's the first line. You basically create a node in isolation. And that node will happen to be the last node in the chain. But we're now doing that in the reverse order. All right, second line. Right here. We are creating another node called Mark. So what we do is we got Mark. And the node objects, I have it right here. Let me just change quickly. Oh, sorry. Let me just change it to be blue. There we go. All right. So that node there, we're calling the same constructor, Mark and also Tom. This one is important. So that means the element is going to be Mark. But the next one here is going to be Tom. So that means the next is assigned to Tom. So the next here is going to be pointing to wherever Tom is pointing to. This is a very critical step. Okay, make sure you get it, please. That one there is pointing to wherever Tom is pointing to. And this part here is going to be Mark. I'll pause right here. Any questions about how this constructor call here is going to set the same node at the same time? Everybody's good? Okay. All right, next one. Similar. So what we do is ln over here, and then we're just going to create ln. Okay, let me just bring that notes once more. Okay, so for that one there, okay, let me just change that over here. Okay, that should be pink. There we go. And that one there you can see is ln and also pointing to wherever Mark is pointing to, right? So that means over here it should be set to Mark. So the next should be pointing to wherever Mark is pointing to. And the element here should be ln. So just 3 lines, and we got the chain of nodes over here. But you might be wondering, just before that, let me also talk about aliasing. One example would be, if you try to look at the Tom objects, apparently you can either try to get to this object by just Tom, or you can get to it by mark.next, or you can get there by ln.next.next. Similar to what we discussed. Okay. Number 2, it could be mark.next. Number 3, it could be ln.next.next. Any questions? All good? Let's now play with this approach one a little bit. Is it possible to say we still want to set the next reference for when we create the objects in the constructor, but we want to somehow swap the order of the creation? Is it possible? Let's now take a look at that. So what I would do is, let me just copy this one here, just as a reference. And then let's create a new page. And we're still talking about approach number 1. All right. And we still want to create a list, a chain of nodes, ln followed by Mark, followed by Tom. Let's say I do the following, right? You can think about it as I write it. Let's say I want to create ln followed by Mark, followed by Tom, the reverse order. Okay. Node, ln, node, Mark, node, Tom. Each one of them is going to correspond to some constructor of the node class. New node. Also, new node, right? Keyword. And let's put the name first. It would be Alan, also Mark, and also Tom. The next for Alan should be Mark. The next for Mark should be Tom. And the next for Tom should be null. Is this going to work? So do you think this might be a runtime error, like an exception, or give you something else? You're getting definitely right track. I want to be a little bit more precise. Guys, here's a question. Is this going to be like a runtime error, for example, some like kind of exception, or something else? Important, that's why I'm mentioning this.
Is it a compile error? Because you're referencing something that's not been created.
Exactly. All right. It's not a runtime error. Runtime error means you can at least execute the code. This piece of code, you cannot even execute it. Why? Because you can see that now I'm referring to Mark. But at this point, Mark was not even declared. It's like declared after this. All right? compilation error. Because mark not declared before its first use. Right, just remember when you do programming, compilation first before you get to the runtime. And once you get to the runtime, in the execution, you may have array index out of bound exception, null pointer exception, etc. Right? But before that, your code better compile. Important. Okay. Let's now get to approach number 2. Okay. Let's say the reason I want to mention this is this kind of a construction here, like I want to build Alan, Mark, and Tom, but somehow I have to create Tom, Mark, and Alan. Seem to be kind of counterintuitive. Is it possible for me to create just the nodes by the order I like? It is possible, but I just got to set the reference more clearly. But let's see the approach number 2. I personally prefer approach number 2, even though you got to write a little bit more lines of code, but just a little bit clearer. But feel free to actually choose this version whenever you have to write. But I got to know both. Approach number 2 right here. So we still got our node class over here, but now we're going to create Alan, Mark, and Tom right here in isolation. The next references will all be null. No connection whatsoever. And then we're going to set the next later. So I'll make it a little bit more efficient for us. Let's say this part here, just about creating the 3 nodes. You can think about, we got Alan here. Okay. So that will be, just bear with me, I just want to be precise. The node, we got elements, and then we got next. Okay, let me just copy that. Okay. Actually, okay, I got 1 here, I got 1 here, right? We got 3 nodes in total. And I also got Mark, and I also got Tom. And the element here, you know the string. That one there, I know the, we don't need to, right? The element. But the most important thing is about the references. You can see it's null, null, and null. That's after the first 3 lines. No connection whatsoever between these 3 nodes. And if we try to do the next 2 lines, Alan.setNext. So the way to think about it is we're calling the setNext method right here. And Mark. So this means this will be Mark. So the next for Alan, rather than here, is now going to point to where Mark is pointing to. That's what that line will do. Similarly, here, the last line, Mark.setNext to be Tom, similar. We're still calling the same method setNext over here, but now the next will just be Tom, right? So this will be Tom. So Mark.next, rather than pointing to here, is going to point to wherever Tom is pointing to. So this chain of nodes here, identical to this chain of nodes, exactly the same. Okay. Yeah, whichever you prefer. But in the test or in the exam, you definitely should know both, right? To answer questions. Okay, let's move on. I also want to show you something interesting right here. Okay. So there is also a way to really write a single line of expression to create a chain of nodes. It's also possible. Okay. I think it's worth mentioning. You can definitely apply that to your assignment as well. So this one here is more to do how we make use of anonymous objects. Already down, it's something you kind of learn maybe in the first years, 2030, but it's good to brush up. So we talk about anonymous objects. Objects without a name. Let's say we still want to create Alan followed by Mark followed by Tom, let's say. What I can do is I can say note Alan equals new note. And then I put Alan here. You can think about up to this point. What I'm doing is I got Alan basically pointing to this node objects right here, where the elements is Alan. And the next is to be determined, which I'll show to you. So this one here would be Alan. Right, so far so good. Now, rather than declaring Mark, I can use anonymous objects. So what we're expecting over here is some note objects, because if you look at the constructor here, the second argument is expecting note. So what I can do is anonymous object without a name. What I will do is new note. Let me move that over here. Well, just remember there's a second argument. New note, and then it should be Mark. So what's been done so far? Next is actually going to point to another new note right here. But we don't really know its name. We just fit it in. That one there is actually a note objects. Again, we got next and elements. The element here is Mark. And the next for Mark will be another new note. That new node should be Tom. Up to this point, we are basically creating another reference. The next reference should be pointing to this node objects. Node. Of course, this can go on and on and on, depending on how long the chain is. So here we got elements and we got next. Let's say, well, apparently we want to be the last node. How should we close it? Put a line. No? Okay. And then, if you simply write it, it's not going to compile. You're not having matching number of brackets. How many brackets should I put to end it? 3, because 1, 2, and 3. Close the orange, close the green, and close the blue. So this is a one-line construction. I'll encourage you to actually try this one here, because I think this is also very useful. We are just using anonymous object in a very good way. But let's talk about some drawback right here. So this tells us in order to get to the green node, we used to have a reference over here called Mark. But if you follow this way, it's not there anymore. The only way to get to the green node is relative positioning. You're going to say Alan.next. But what if I really, really want to get a reference to this? What should I do? Aliasing, right? I can say node Mark equals Alan.next. That way, I will be able to use the Mark name for later, if I want to. So what this will do is, this Mark is going to point to wherever Alan.next is pointing to. So in that way, I'm creating this alias. And you can do the same to create another one for Tom if you want to. But you don't really have to, only if you want to refer to some specific node. All right, question about this. Anonymous objects. I think that's pretty cool. Okay. Okay, we do have some little bit of time. Let's see what we have over here. Actually, that one's done. Okay. Okay, awesome. You know what? I think I'll end here because the rest is really something that's already covered. I can do that as a recap. So please, before Thursday, review this. Make sure you understand about linked list conceptually. We're going to solve some methods implementation together on Thursday. All right, see you.